All right, give me a second, guys. I need to go do a thing. All right. All right, folks. So sorry about that. I had to go take care of my markers and such. So you've got an exam coming up on Monday. That exam's covering chapters 23, 24, and 25. So let's give you a sense of what I expect you guys to know. So for chapter 23, the big concept was Faraday's law of induction. Somebody tell me what Faraday's law of induction was.
Was that the negative delta I over delta t or something like that?
Close. It's not an I, it's a
Flux.
It's a P.
yeah. So Faraday's law of induction talks about the induced EMF. Right? EMF is just a fancy schmancy word for a voltage. So basically what it means is that if you've got some flux and that flux is changing over time, then that suggests that you're going to get a voltage in response. And the minus sign says that it's going to try to fight the change. So if you try to make the flux through a surface be larger, the way that surface is going to respond is by making the flux or by making an EMF to try to keep the flux the same. If you try to make the flux smaller, it'll make an EMF in the opposite direction, trying to keep the flux the same. No matter what change you try to make, the induced EMF is always going to be in the opposite direction. So it's going to be critically important you guys understand how to apply this and that logic, because there'll be lots of questions about that. What the heck is flux? If I have to worry about how it's changing, I should probably know what it is. So what the heck is flux? Don't all jump up at once.
Is it how many, I don't know what it is, but how many kind of lines go through the magnetic field?
Well, it's how many lines go through the surface. The lines are
Okay.
the magnetic field.
Okay.
So if I've got, let's say I'm talking about this piece of paper, right? What's going to happen is I'm going to have magnetic field lines that can penetrate that piece of paper in different locations. Magnetic flux is basically counting how many lines I've got. And the way you formulate that is you say that the flux is equal to the magnitude of B times the magnitude of A times the cosine of the angle between B and A. What the heck is the direction of A? How can I find the angle between B and A if I don't know the direction of A? What is the direction of the area vector?
Isn't it always perpendicular?
It's always perpendicular to the surface. So if this piece of paper was my surface, the area vector would be pointing out of it towards the camera, right? If your screen that you're watching me on was the surface, the area vector would point out of the screen toward your face. And so that's how you calculate the flux. If that flux is changing, either because B is changing or because the area is changing or because the orientation of the two things is changing, then that implies that Faraday's law will create a response, a voltage in response to that change. So we spent some time talking about that, working through that. We got a couple homework problems about motional EMFs. Motional EMFs just happen because this is changing over time, and you get VL times V. So the idea is that if I've got a magnetic field that is uniform, say, here's B everywhere, and I've got some surface that lives inside and is therefore got flux going through it. If I pull it out with a velocity V, as it leaves, the amount of flux inside that loop gets smaller because as it leaves, it's going into a region out here where there is no magnetic field. And if that's the case, there's an induced EMF that's going to try to keep the flux the same, and that's going to fight me as I pull it out. All right, so that was motional
Is it
EMF.
the EMF leaving?
That's the EMF you get when you pull out of that magnetic field.
Okay.
Yeah. We also did generators. If I have a generator, then what's going to happen is I've got usually a magnetic field and a coil moving around in a magnetic field, and that coil rotates with time at a certain angular velocity. And we found that the EMF induced in that coil was going to be N times B times A times omega times either the sine or the cosine, doesn't matter which, of omega t. A lot of times when you use this, you don't even care about the omega t part. You often only care about the maximum part, which is this stuff right here. That's ring any bells?
Yeah, kind of.
So from there, once we had sort of the grounding and the basic ideas of flux and EMFs.
I actually have a question, Dr. Fleming.
Yeah, what's up?
So the E equals BLV.
Mm-hmm.
You said that was for outside of the magnetic field?
No, it's called a motional EMF. And it happens when you move an object around in a magnetic field that's not uniform. So here, I'm moving this loop around, but I'm in a place where there is a magnetic field, and I'm moving to a place where there's not a magnetic field. And as I'm emerging from one place to the other, I will get an EMF in response.
So
I talked about this the other day. Remember, I almost always end up going on the Ghost Hunters rant. I have to be careful. My wife's upstairs, so she can hear me.
okay.
but my wife watches a lot of ghost hunter shows, and on ghost hunter shows, they often have EMF
Oh
detectors
yeah.
that they wave around. But what's going to happen is as they move them around, what they're doing is they could be moving from a place where there is a magnetic field to another place where there's not a magnetic field, and they're going to get a response on their meter just from moving around. This tells you how much of a response you get.
So okay, because I think that's the issue I had before because it was like 3 different types of EMF things. So like when you ask us a question on the exam, will you kind of like tell us, what we're like looking for?
Well, you've got to use, basically what's going to happen is
Mhm.
the only formula that we're really using is this.
Right.
What's happening is under certain circumstances, this turns into this.
Okay.
Right? If I've got a coil that's spinning around in a magnetic field, this
Mhm.
turns into this.
Okay.
Right. So the big picture is this thing. This is just how you implement it in some particular scenarios where it's important to be able to kind of translate it. But it's not like it's 3 different equations. It's
Mhm.
one equation. It's just that under certain conditions, like when you're pulling a loop out, this simplifies to this.
Okay.
And when you're spinning a loop inside a magnetic field, this will simplify to this.
Okay.
And to prove how you go from here to there,
Mhm.
I'd have to use some calculus, which we're not going to do.
Okay.
But that's why it seems like it's 3 different equations, but really it's not.
Right. Okay.
So you just got to know what conditions these are used for before you pull them out. But this, always true.
So Dr. Fleming, for E equal BLV, it's every time the EMF in the magnetic field is not uniform. So
Correct.
how can you formulate a sentence so we can know about it? Are you gonna tell us?
How would that look in a sentence?
Yes.
You'd have to have a problem where I say I've got a blah 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 size object that's being removed from a magnetic field with a speed of blah blah blah.
Okay.
Right.
Okay.
So that's what you'd be looking for. One of your homework problems, I think, had a person pulling their hand out of an MRI machine. Right?
Oh, really? I don't remember.
I thought so. But you were finding like the induced EMF or the induced current in somebody's wedding ring was one of your homework problems.
Wedding ring.
I think so. So I'm going back. Let's search for it real quick. I don't think I pulled it off this year. So looking at chapter 23, let's look at this very first one. Oh, nope, not that one. Maybe I pulled it off this semester.
No, there wasn't anything about a wedding ring. That in chapter 23, we didn't even use BLV.
Okay, I may have pulled those questions off because I usually don't.
Yeah, I don't.
Okay.
Yeah, you didn't. I'm looking at my notes now. You didn't.
Yeah, I usually don't spend a lot of time on motional EMFs.
Um,
It's a very specific.
We only use those 2 formula, but not E
Okay,
equal.
so don't worry about it.
Okay.
okay.
Yeah. But anyway, that like in a problem like that, like I was doing the wedding ring problem, I'd have to tell you, say, here's the diameter of the wedding ring. So I'd have to tell you like the radius of the wedding ring. And the idea is that it goes from a region where there is a magnetic field to one where there's not a magnetic field. So what's going to happen is the flux is changing. How do I find the flux? VA cosine theta. Usually theta is such that this equals 1. And I'm going to go from where there is a field to where there's not a field. So the change is going to be this, but negative. And I'm going to do it in a certain amount of time. So divided by delta t, and that'd be my EMF.
Okay.
So that's the sort of way that that works. But in that problem, I had to give you some information about how fast you pull your hand out. So I'm either going to tell you the velocity you're pulling your hand out with, or I'm telling you the time it takes to pull your hand out, either way.
Does that say sine theta?
No. Or wait, up here, you mean?
No. Where it says negative BA.
No, it's cosine.
Oh, okay.
So we had to introduce Faraday's law. You should be familiar with Faraday's law and be able to work through the implications of Faraday's law. You're going to want to pay particular attention to the sign convention so that you can tell me the direction of those changes, because you better believe on a take-home exam, I'm going to ask you lots of questions where you have to figure out the direction of a change and justify your answers. Just to see if we're on the same page here. Imagine that this piece of paper has a magnetic field going through it, and that magnetic field points up with an angle of 30 degrees with respect to the horizontal. So it's coming out of the page, but coming out of the page at a 30-degree angle. How much flux am I generating in that page?
How much flux?
Yeah. So again, let me write down in words what I'm asking you so that it's clear. So I'm telling you I have this piece of paper, and of course the paper is 8.5 by 11 inch paper. There's a magnetic field, let's say that it's 2 Tesla, but it points at 30 degrees from the horizontal. So in other words, if this is my piece of paper, the magnetic field is not coming straight towards the camera, it's coming straight towards the camera, and this angle right down here between the horizontal and the magnetic field is 30 degrees.
Right.
Got it?
Mm-hmm.
How much flux do I have?
Is that 85 or 8.5?
8.5, it's standard letter size.
You say inches?
Do what?
Is it inches or?
Yeah, those are inches.
Okay.
I usually hate using inches. So if I wanted to convert that into centimeters, I know that 1 inch is 2.54 centimeters.
Right.
So if we go 8.5 times 2.54, it's 21.59 centimeters by 27.94 centimeters. So my cross-sectional area in square meters is going to be 0.0603 Let's keep an extra sig fig. So there's my area for that piece of paper. How much flux am I getting?
We are 2 times point.
Let me know when you have an answer.
Point 104?
Nope.
No.
How'd you get 0.104?
I multiply 2 by A
Okay.
by 0.06 times the cosine of 30.
Except here's the problem. 30 is not the angle you want.
So 30 is the angle for the horizontal and B.
Yeah.
Okay.
So what's going to happen is here's horizontal. That's the plane of the paper. Here's the magnetic field pointing out of the plane of the paper. And this angle right here is 30 degrees. But the cosine of theta that I need in this equation is the angle between the magnetic field and the area vector. The area vector points straight up. So
So it
the
would be
red
60.
pen, yes. So
Why is it 60?
because the angle I gave you, here's the magnetic field. This is the blue pen, right? The angle I gave you is this angle down here is 30 degrees, right? However, the area vector points straight out of the paper. That's like the red pen.
Right.
So the angle between these is the actual angle that I want. That's not 30, but I do know that this angle plus this angle has to add up to 90 because that's going to be a right angle.
Right.
So I actually want to use 60 degrees.
And I got 0.0632.
Yeah. Well, 0.06032. But yes.
Okay.
Because what's going to happen is when I do the
Oh.
flux,
Yeah.
it's going to be B, which is 2, times A, which is this, 0.06032, times the cosine of not 30, but 60. But this is a half. A half times 2 cancels. And that was my flux. So be prepared to do questions like that where you have to figure out the direction of stuff. It will matter. Let's go one step further. Let's imagine that I take that magnetic field that I mentioned in this previous problem, and over the course of half a second, I turn it off. What's the induced EMF in the edges of the paper?
Wait, repeat that?
So I've got this magnetic field, same setup we had for this problem, except that over
Half a second.
half a second, I turn the magnetic field off.
Wouldn't you just divide the number?
So
that you-
B is gonna be negative.
So what is the induced EMF in the paper from that?
Would that be 0.12?
Why 0.12?
Because I had divided by half a second. By 0.5.
But B becomes negative, right? Because we turn it off.
Well, so this is where I usually ignore minus signs and I think about direction for a second, because on your exam you're going to have to not just say plus or minus, you're going to have to tell me what direction it is. So I do know that my induced EMF is going to equal negative delta phi over delta t, right? And phi is going to go from being this before to being 0 after. So the change is going to be this, and it's going to be negative because it's going down. So it's going to be positive 0.06032 divided by 0.5, which, as Wilson pointed out, is going to be 0.12 something.
Yeah, 0.12064. Oh.
And that's a voltage in volts. So that gives me the magnitude of my EMF. That's fine. But what about the direction? Simply saying that it's positive is insufficient. I need to associate an honest to God, you could point in that direction for this EMF. So what direction would that EMF be in?
To the right?
Nope.
No.
The
left.
to the right is an answer that doesn't make any sense for this question.
Okay.
Right. Oh God.
In fact, there's only two words that could possibly answer this question. Only two.
Can we say that it goes down?
Nope. Down is not one of the two words that it can possibly be.
Clockwise?
Clockwise and counterclockwise. You know when
Oh.
you see this, it's one of those two things.
Oh, okay.
Uh,
It'll be
Which one's it going to be?
counterclockwise.
Counterclockwise.
Counterclockwise. How do I know that? Well, I could do it the less common sensey way. If I'm calling this the positive Z direction, and I got a positive answer, that means it's going to flow. If I stick my thumb in the direction of the flux, it's going to flow in the direction my fingers curl. That's one way to think about it. The other way to think about it, the way that I usually do it, is that my magnetic field was causing flux out of the page, but that flux was going away. So what the induced EMF is trying to do is to keep current flowing to make a magnetic field be upward. And that happens when it's counterclockwise. Does that make sense?
So
Mhm.
because the flux was positive and it's now going negative, that means it's coming out from the back. The EMF still want him to be positive.
Correct. Yeah. The magnetic field was coming out of the page. And
Right.
what was happening is it was going away. And so the page is like, no, I can't let the magnetic field go away. So it wants to create its own magnetic field to keep it up. And
Right.
in chapter 22, if the current goes counterclockwise, that'll make a magnetic field pointing out of the page. So that's what's going to happen is when you try to turn the field off, it's like, no, I need to keep it going.
Okay.
So, being able to deal with conceptual questions like that, probably going to be more important on this exam than it would be on other exams. Because those are the sorts of problems where it's more difficult to cheat, or at least to cheat in a way that's reliable. So from there, we should probably talk about inductance. What do I mean by inductance?
Oh, snap, I forgot all about. Oh, that's right there.
That's the definition of inductance. So the idea is that if you've got, say, a coil, and you're changing the magnetic field in that coil by changing the current in that coil, what's going to happen is when you try to make the current bigger or smaller, you'd be changing the magnetic field, which would change the flux. And Faraday's law says the coil is going to fight you when you do that. So if you try to make the current larger, it's going to create an EMF that pushes back against you, trying to keep the current small. If you have a current that is getting smaller, that means your magnetic field will be getting smaller, and the EMF of the coil will fight you to try to keep the current going. And the L is just the part of this response that depends on the size and the shape of your inductor. For a solenoid, the inductance was it U naught N squared A
Over
over
L.
L, right?
Mhm.
And even for other shapes, the general point is that it looks pretty similar. The bigger your shape, the larger the area, the bigger inductance it's going to have. The longer it is, the less inductance you're going to have. But it's extremely sensitive to the number of turns. So if you double the number of turns, you will, in general, quadruple the size of your inductance. It will fight you harder when you have lots of loops because each of those loops is contributing the same amount to the total flux, and it doesn't want the flux to change.
But
Right.
does it change itself? Like if the current is going down and the magnetic field is going down, but the EMF is against it.
I'm trying to think of what you mean by that.
Like if the EMF is against the current changing its direction,
Okay.
but for the EMF to be against it, does it change itself or?
So for instance, here is an AC circuit with an inductor in it. Maybe it's got a resistor too, I don't care. Now what's going to happen is this AC voltage is changing over time. But when you look at the current, when the current comes out, it's going to be getting bigger and smaller and bigger and smaller. And what's going to happen is when the current is big, I've got a lot of magnetic field inside that coil.
Right.
And so I think what might be confusing is that the EMF that we're inducing is the voltage across the inductor, not the voltage across my power.
Oh, okay.
Right?
Okay.
So what's going to happen is there's going to be times when the current is going forward because the power supply is trying to pump current through that circuit. But what's going to happen is if you're trying to make that current be bigger, then the voltage across this inductor is pushing back the other direction. We call it a back EMF.
Okay.
Right? So what's happening is this guy is fighting against your power supply, trying to keep the current from getting bigger.
Okay.
But then eventually when the current maxes out and starts to drop again, now what's going to happen is your power supply is trying to send current the other direction. It's going to fight that too.
Okay.
Does that make sense?
Yes.
So when you're trying to make the current bigger, the EMF of the voltage of the inductor is one direction. When you try to make it smaller, the EMF is the opposite direction. And it's always fighting you no matter what you do.
Okay.
Right? You learned how to do RL circuits, which is where you don't have an AC battery, you have a DC battery, and they're going to behave very much like capacitor circuits. And the current is going to be a function of time. Right. This first is while you're charging up. This is while you're discharging. And we solve problems of that nature. And then we learned how to do AC circuits. And in AC circuits, you had to learn about things like the impedance. Or the phase shift. And the idea was that this phase shift tells you whether the current in the circuit is lagging or leading the voltage of your power supply. So it could be that what's going to happen is if your red line is your current, the voltage of your power supply might be a similar thing, but it's shifted forwards or backwards by phi, right?
Mm-hmm.
So you had several problems in AC circuits. probably expect that AC circuits will be heavily represented on the next exam. So those are the big ideas in chapter 23. Question?
Yeah. Is it? Never mind. I found it. I was just wondering if it was XL minus XC over R, or is it?
It is XL minus XC over R. That's correct.
Okay.
And of course, how do you find XL? XL and XC?
XL is W. Yeah, XL is 1 over L. Oh, shit.
Right. What do I mean when I say omega?
2 pi F.
5.
And would the F always be constant in that, or?
Usually for problems I'll be asking you, I won't be changing the frequency in the middle of the problem.
Okay.
Usually, yes. Right. So that was the big concepts from chapter 23. Chapter 24 introduced electromagnetic waves. What do I expect you to know about electromagnetic waves?
They're everywhere.
That's a true statement, but probably not the extent of what I need you to know. The big thing is being able to write down the equation for an electromagnetic plane wave. If I said I needed an electromagnetic plane wave whose maximum electric field was 50,000 newtons per coulomb, and it has a, let's say, a wavelength of 450 nanometers. Could you write me an expression for the magnetic field as a function of time?
Is that the Y equals A
E0.
sine KX plus or minus WT? Okay.
Yep.
Just checking.
So what would my expression be for B as a function of time?
The function of time.
B equals B.
So far, you're
B,
correct.
B equals B naught sine KX plus or minus WT. Will be initial.
So far, so good. But let's fill in some blanks. Do I know what this? Or not 4 pi. Do I know what this or K or this is? Do I know what any of those things are?
No.
Can I figure them out?
K is the wave number.
Can't find K because K is 2 pi over the wavelength.
Ha! And the wavelength was given. So for this problem, K is going to be 2 pi divided by 450 times 10 to the negative 9th. That's a number that I can fill in the blanks with.
And E is equal to C over B. Hold on. So you can find B0 because E0 is equal to the speed of light divided by B0. So you can find B0 for that.
And then we already know the W is 2 pi times the frequency.
Yeah. So we know that V equals F times lambda. So F is going to equal V divided by lambda.
Is V a constant?
Is V a constant?
Yes, it's the velocity, right?
Yes. But what's the velocity of light?
Oh, okay.
2.99 times 10 to the 9th.
10 to the 8th, but yes.
Oh, 8. Okay, 8.
Yeah, piece of cake. So that's how I was able to figure out this. I took 3.99 times 10 to the 8th divided by the 450 times 10 to the minus 9, and I get 21.4 hertz.
Right.
So then I can use omega is 2 pi times f. I get omega is 135. Problem though. I gave you my maximum EMF or my maximum electric field, but not my maximum magnetic field. How would I find the maximum magnetic field?
So it's gonna be the speed of light. Hold on. Multiply by E0 equal E0 C. So it's gonna be E0 divided by the speed of light to find B0.
Right.
Gonna be 50,000 divided by 2. It's 1.67 times 10 to the 12.
No.
No.
I take 50,000 divided by 2.99 times 10 to the 8th. You get 1.67 times 10 to the negative 4th. I suspect you probably had an issue with your calculator because
Oh, I put a wrong number. That's why.
So, from stuff in chapter 24, you should definitely be able to write or interpret something with an electromagnetic plane wave. I'm also able to relate the electric or magnetic fields to the intensity. In this problem, what's the intensity of this beam?
Intensity.
Power.
I equals P over A.
That's a true statement.
We don't have A, but so we can use I equal E0 B0 divided by 2 mu 0.
That would work.
Okay.
All right. You had like two other formulas you could use. Like if it was me, I would have used power equals 1/2 C epsilon naught times E naught squared. I would have just done it that way.
That's an equation we got?
Yep. There were three equations for the power of an electromagnetic wave. There was another one that was B naught squared over, is it CB squared over 2 mu naught, I think?
Yes.
And then the other one is the one you just cited, where it's E naught V naught over mu naught. And which of those three equations is useful at any given time is going to depend on which of those things you know, which ones you don't know.
Okay.
But in terms of stuff from chapter 24, that's pretty much it. I can't really ask you to do too much. I might ask you questions regarding them, involving your understanding of how the electromagnetic spectrum works. For instance, if I asked you about, high-powered microscopes, imagine that I want to make a microscope that is a non-optical microscope that's intended to observe cellular organisms, right? Single-celled organisms. And I told you that these would work best if the wavelength of light that we used was comparable to the size of a cell. What kind of light should I use for this microscope?
Hmm.
Well, how big is a cell?
Extremely, extremely small.
Yeah, I'm looking for numbers. You guys are biology majors. You tell me, how big is a cell?
Oh.
I don't think they tell us. I don't think they really tell us.
Yeah, you don't spend a lot of time paying attention to it. I seem to recall once seeing an illustration of a red blood cell. And that red blood cell was kind of like a little frisbee shape. And I seem to remember it being about 7 microns across. But let's just check.
That is something they did not speak about.
So I'm going to Google the dimensions of a red blood cell. So according to this, a typical human red blood cell has a diameter of between about 6.2 and 8.2 micrometers at its thickest point. And in the center, where it's kind of got that little divot in the middle, it's a little bit thinner. But let's go with that diameter. Let's assume that it's between 6.2 and 8.2 microns. And I want to choose light to view this red blood cell. What wavelength of light should I pick? And what color would my laser be?
Dr. Fleming, can you write it down, please?
Trying to save my last sheet. 4. Yeah. So I've got a red blood cell. Let's call this thing 8.2 micrometers in diameter. So based on that, what wavelength of light should I use to observe that? Assuming that I need a wavelength of light that is comparable to the size of the thing that I'm measuring.
Right.
So I want my wavelength to be about 8.2 micrometers.
They're gonna be, yeah, kind of.
Would it be delta L equals M times the wavelength? No. I got it.
Well, so let's just think about this for a second. And let me switch my share for a minute. So let's do a little quick check on some stuff. What am I doing, stupid? I don't want to share the camera. Stop it. There we go. So let's go with this. So I'm just going to take, here is a nifty little, come on. There we go. So I'm looking at wavelengths that are comparable to the size of my cells. The cell I'm trying to image has a wavelength of 8.2 micrometers. But what about the wavelength of my light? Well, what kind of light is going to have a wavelength of about 8.2 micrometers?
Yeah, visible.
Pretty close. Here you can see that they've got the midpoint of my visible light being about 0.5 times 10 to the minus 6. So
It'd be
I'm on the same order
ultraviolet.
of magnitude as that, right? And in fact, usually when I think about the human visible range, the numbers that I kind of know off the top of my head is that the visible range is from about 400 nanometers to about 750 nanometers. How many nanometers is that?
Would it be like another third smaller?
Well, how many micrometers are there in a nanometer?
3.
Times 10 to the negative 3.
Positive 3.
Positive. Yeah, 3.
100 nanometers. So the wavelength of my light is longer than anything in the visible range. So I don't want to use that.
Okay.
So instead, 8200 is going to be longer than the upper end of my electromagnetic spectrum. So do I want to use what kind of light?
The next one was ultraviolet.
Yeah. Well, ultraviolet would actually be lower than this. Remember, longer wavelengths means higher frequencies. And so if you go back to the screen share,
Would you on like the test, would you like give us this little chart or something, or this is
well, it's a take-home exam. You could Google that stuff. You could look at the book.
Okay.
or
Part of why I'm asking this question now is that one of the things that I have to do is I have to ask you more open-ended questions where you have to think about the answer and probably can't just Google it. Does that make sense?
yeah.
Yes.
And so the kinds of questions that I'm going to throw at you are going to include some things that I don't normally throw at you, because I would never ask you this question on an in-class exam, because I don't necessarily expect that you have memorized like what the electromagnetic spectrum looks like, or that you have memorized what the visible range is. But I feel a lot more comfortable asking that question on a take-home exam, because that's the sort of thing where you're like, I don't know exactly what the upper end of human vision is, but I can always look that up. And so there are some kind of questions that are more open-ended that I may have to throw at you. So I'm trying to kind of prepare you for that, because it'll be a little bit different.
So would it be in between visible and ultraviolet?
It'll be between infrared and radio, or I mean,
Yeah. So what's going to happen is, for the red blood cells, at least, it's actually infrared.
Oh,
Your red blood cells are bigger cells, apparently. But that's the kind of thing I'm expecting you to look at. So in terms of chapter 24 and 25, there's not much I can ask you. There's only so many questions I can give you. All right, what about questions 20 or chapters 25 and 26? There's going to be all kinds of optics stuff. What kind of optic stuff do I expect you guys to know?
converging lenses, diverging lenses.
Yeah, you should be able to do converging or divergent lenses or mirrors. You should know all of the sign conventions, and be able to use the thin lens equation. Please note that I will intentionally be choosing problems that require that you be aware of your sign convention. And I will try to throw questions in there that if you screw the signs up, you'll get it wrong. Because that's how I'm going to differentiate someone who just sees a formula and someone who knows what they're plugging into that formula. Does that make sense?
Yeah.
So if I were to have, let's say, a two-lens system where this is a diverging lens, heck, let's make this a mirror. And I have a diverging lens and a converging mirror. And I place them 10 centimeters apart. And I place an object. Let's say this has a focal length of magnitude 10 centimeters. This has a focal length of magnitude 15 centimeters. And I place an object 5 centimeters in front of the first lens. You should be able to tell me where the image forms and what the magnification of the image would be. You could also tell me whether the image was real or whether it was virtual, and the magnification of the final answer. How could you do that?
We're gonna find I first for the diverging lens. It's gonna be 1 over minus 10 equal 1i plus 1 over 5. I equal.
So we're working through this. Place that there where I can still see it.
We're gonna have to find O.
That's
Now, what is O?
5.
Yeah, O is given.
Okay. We don't know I.
Class and they're still dancing.
So the first,
I give up. All right. So you're going to have 1 over F. What is the F for the first lens?
negative 10.
Negative 10. It's equal 1 over I, which in this case is, or 1 over O, which in this case is 5, plus 1 over I. So far, so good?
Yes.
Hey, it's negative 10 because we have a diverging mirror, right?
A diverging lens.
Lens, yeah.
Yeah, you have to know the convention because I'm not going to tell you, oh, this has a focal length of negative whatever. I'm going to tell you it's a diverging lens or a converging. And you're going to have to know what to do with the signs based on that.
Okay.
So I move this over. I have negative 1 over 10 minus 1 over 5 equals 1 over I. That one's easy enough. I can do it in my head. It's going to be negative 3 over 10. Which means negative
I.
3.33 is equal to I. So far, so good?
Mm-hmm.
Now, what's going to happen is the image from that first object, or from that first lens, is going to have to become the object for the second lens.
Okay.
So when I do the second one, I'm going to have 1 over F, but what is F? It's 15. Is it positive or is it negative?
Positive.
Positive. That's going to equal 1 over O plus 1 over I. What the heck is O going to be for that second lens?
Would that be 15? Or would it be 10?
It would be neither of those.
Oh, okay.
So to see what the answer is going to be, let's go back to my original drawing. So we found the image from that first lens to be an image distance of negative 3.33.
Mhm.
So where on my picture is the image?
The image is on the same side as the objects.
Yeah. So the image is over here, 3.3 centimeters, right? Had I gotten a positive 3.33, it would have been over here 3 centimeters.
Right.
But now this image is the object for this mirror. So how far is it from this image to this mirror?
Is it 13.3?
Yes. Because if this is 3.33 and this is 10, if I add them together, it's 13.33. So now what's going to happen is I'm solving that for I. So I'm going to have 1 over 15 minus 1 over 13.3 equals 1 over I. That's going to give me a negative number because 1/15 is going to be bigger than 1/13. So I end up with negative 119.7 is equal to I. So far, so good?
Yeah.
Mhm.
So this is where I kind of get confused at. So would this picture be on the right side of the converging mirror or on the left side?
So, first of all, is this an image? Is this image real or virtual?
Oh,
Virtual.
It's virtual. Why? Because I got a negative image distance.
Right.
Now, the rules for lenses and the rules for mirrors are different.
the opposite, right?
Yeah. If this was a lens, having a virtual image would have meant the image would be on this side, right? But for mirrors, virtual images appear on the other side. So what's going to happen is my object is going to appear to be behind the mirror 119.7 centimeters.
Okay.
Now, what is the magnification of this whole shebang? Well, what's going to happen is I have to find two magnifications. One, the magnification from the first lens, and the second, the magnification from the second mirror. In either case, the magnification is negative I over O. So for the first lens, the magnification was negative 3.33 over O, which was, for that one, 5. The minus signs are going to cancel, meaning that the original image was upright, and it was going to equal 3.33 divided by 5. It was 2/3 the regular size. Call that M1. Is everybody clear on where I'm getting that?
Yeah.
Yes.
Now, the second magnification is going to be negative its I, which was negative 119.7, divided by its O, but its O was 13.33. Notice the minus signs are going to cancel, so my image is going to still be upright. But it's going to be a whopping 8.98 times larger.
You said upright.
It's upright because I got a positive answer.
Okay.
Right. So now my total magnification is going to be just the product of my original magnifications. So I take 8.98 times 0.667. And so the image that I get is going to be almost 6 times bigger than the original object. It's still right side up. It's a virtual image, but it's going to be way, way magnified. So again, be prepared to answer questions like that. I will definitely be choosing those questions in such a way that it'll matter what the sign conventions are. And I am particularly fond of multiple lens systems because that's going to really trip people up. A lot of people will do a problem like this and they'll make the mistake of getting the first I and then they would plug in 3.33 for the next O, and that is incorrect. How are you feeling?
Good.
On a scale of 1 to 10, how fearful of this exam are you?
10.
No, 8.
Okay.
We just don't know what you're gonna put on this because you've never been in this and we've never been in this.
Well, the good news is I haven't been in this either, so I'm not really sure yet. Usually at this point in the course before an exam, if I haven't already written the exam, I know what I'm going to ask. I just haven't settled on the numbers yet. I'm not sure yet. I'm going to have to spend that weekend figuring out what I'm going to ask. And what will end up happening is I'm going to have to write like a gazillion questions because there's going to be multiple versions so that you don't all have the same questions. So I don't know, but those are the sorts of things that I expect. I mean, I definitely expect you're going to have some optics questions where you're going to have to answer some tricky bits with optics. I definitely expect there's going to be some problems where I have you thinking through the direction of induced EMFs, because that's going to be one of those things that you can't quite just Google your way into the answer. You're going to have to be able to think through the logic. And those are the kinds of questions that make sense in a take-home exam sort of scenario.
We just want you to help us help you.
Well, you can help me by doing your homework and passing my class.
Of course.
Yeah, that is the thing I want all of you to do, is to do the freaking homework, because that's the number one thing that's going to prevent people from getting out of here in one piece. All right, where do we need more work? Because otherwise I'm going to go away.
I have a question on 25.4.
Okay, let's take a look at it.
Yes, thank you.
So we're looking at, you said 25.4, huh?
Yes.
Let's work through that. Okay. So what's happening with this problem is you've got an object blah, blah, blah centimeters in front of a diverging lens that has a focal length of blah, 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 blah. But when you do that, you're getting an image that's the wrong size. And so what you're going to want to do is to move the object someplace new and to get a different sized image. So let's just work this through. And for me, I'm going to write down these numbers. I'm going to click away from the screen. I'm told that my object is originally 23.08 centimeters. So let's do it this way. So real quick, let's draw a picture of what I'm expecting here. So I've got, in my original setup, here's my lens, and it says it's a diverging lens, right?
Mm-hmm.
The diverging lenses are thicker at the edges and fatter on the middle. It also tells me that even though they gave me the focal length, the fact that it's diverging means that the focal length is not 11.3 or 11.43, it's negative 11.43, right?
Mm-hmm.
And my object, which I will represent with a stick figure, is 23.08 centimeters away. Now, the first thing I'm going to have to figure out is, where is the image for this guy going to form? I don't even know where the image is going to be. So what I'll have to do is to solve the problem of where the original wrong size image appears. So I've got 1 over F equals 1 over O plus 1 over I. And I'm solving for where the image is going to appear. So it's going to be 1 over F minus 1 over O equals 1 over I. And F, in my case, was negative, I've already forgotten, 11.43 minus O, which was 23.08.
23.08.
Yeah. And that's going to equal 1 over I. Notice I have a minus and a minus, so I'm for sure going to get a negative answer from this. So 11.43, yoink,
Negative
23.08, yoink. So I get that my image distance is negative 7.64 centimeters, right? I just added that up and took the reciprocal. You with me?
Yes.
Now, let's go back to my picture for a second. So in my original picture, well, I thought it would still be there, darn it. Never mind, let's go back to my drawing. So look, my original picture, this was my lens, this was my dude, and what's going to happen is this was 23.08, but my image is a virtual image because it's a negative image distance. So rather than being on this side of the lens, it appears on this side of the lens. So here's my image. And it's 7.64 centimeters away. So I get an image of the dude that's a little bit closer to the lens than the original dude was. And what's the magnification of my dude? Well, magnification is negative I over O. So negative 7.64 over 23.08. So my dude is 7.64 divided by 23.08. Positive 0.330 is my magnification. So my image is upright because it's positive, and it's about 1/3 the regular size. So far, so good?
Yes.
So that, unfortunately, is incorrect. We don't want to have this much magnification. We want my image to be even smaller.
Mhm.
How much smaller? Well, I love
3.3.
a question that says, I want to reduce that size by a factor of 3.3. So I want my magnification to be 3.3 times smaller than 0.331. So I'm going to divide that by 3. And that means the magnification that I am shooting for needs to be 0.110. Fair enough?
Mm-hmm.
So I can't put my object in the same location that I had it before. If I put the object here, I get an image that's the wrong size here. So I've got to move this guy around. So now I'm going to go back and solve the problem again, only this time what's going to happen is my object is I don't know where, and I'm solving for O.
Yes.
But I don't know where the image is going to be either. However, I do know that my new magnification, M, has to equal negative I over O. But if I rearrange that, that says that I has to equal negative O times M. I just solve for I in terms of O. Does that make sense?
Mm-hmm.
So now, once I've got that, I can go back to my thin lens equation and say that 1 over F equals 1 over O plus, 1 over I, which is 1 over negative O times M. And the only variable in there that I don't know is O.
Mm-hmm.
So
Okay.
how do I solve for O?
Would you multiply M?
Well, the thing I'm trying to get by itself is O, right?
Okay.
Mhm.
Number, right? It's the 0.331 or 0.110, excuse me. So what
So
I'm
we
going to
can
go ahead.
we can find the same denominator for those two fractions on the right. So
Yeah.
we can put O in front and open parentheses with.
Yeah. What I would do is, like, when in doubt, let's just murder the denominators, right? Let's just multiply everything in the equation by O. So if I do that, over here, I'm going to have O divided by F. Here, I'm going to have, well, when I multiply this by O, it's going to turn into a 1. And over here, it's going to be minus, well, when I multiply this by O, the O will cancel, and I'll have just 1 over M. Does that make sense? I just multiplied both sides of the equation by O.
Mhm.
And all the things that had an O in the denominator, the O's cancel, leaving behind this. And notice 1 is a number. M is a number. This is a freaking number. So now to get O, O is going to be this 1 minus 1 over M
Times F.
times the focal length.
Okay.
How did you get M?
M
For the
was,
second.
well, because what happened was I solved for the magnification that I had in the original setup of the problem. And the magnification is negative I over O, right? So I found I knew O, I plugged them in and got an answer. But it says in the problem that this magnification is too big by a factor of blah, blah, blah. My case, it was 0.33 or like 3.3. So I divided it by 3.3. So I took this divided by 3.3 and got this. That's my new magnification. I then plugged that in and solved.
Okay.
That's how I solved the problem.
So there was no, since we're talking about the magnification, is there any case where we only talking about the magnification and not where the image should be? Like I is gonna be the same and all we have to change is M, like how big or how small the image is.
No, so what's going to happen is I'll get a different magnification if my image is at different distances, because what's happening there,
Okay.
let me see if I can show you.
Okay. Okay, I see.
I'm going to go back to my trusty rusty simulation where you can sort of play around with stuff. Oh wait, that's the edge. That's why I'm not seeing it. So, yes, I get it. Come on. Yes, I get it. Yes, please do it. All right, there we go. So what's going to happen is you'll notice, like, when I move the object backwards, what's going to happen is by the time the light reconverges, it's gotten more and more off field, and I've gotten a bigger image, right?
Mhm.
When I move it further back, just the geometry makes it smaller. So
Oh, okay.
So I can't change the magnification or the image distance without changing the magnification. And I can't change the magnification without changing the image distance.
Okay.
So that's what's happening there, is that the reason the magnification occurs is because when the image forms further back, the light travels further before it comes together, and that makes the overall size larger.
Mhm.
But when the image appears really close to the lens, or really close to the focal point, it doesn't have as much time to spread out, and as a consequence, you end up with smaller images.
Okay.
So that was a good question. What else we got?
I think that's it.
All right. So just remember, the exam is going to probably go live probably after class on Monday, so you'll have one more shot at asking questions. But I will be talking about other stuff even before the exam. Once the exam goes live, you'll have 48 hours. I think that's what I've settled on. 48 hours to do it. But once you start it, it's starting a timer, and that timer is going to run for 2 hours total. So make sure you don't start the exam before you're ready to sit down and do the exam, right? You know, get that 2 hours of uninterrupted time sort of blocked away before you try to start, because you've only got one shot at this, and I don't want you to screw that up.
You said it's available after class on Monday?
That's, I think, when it's going to go live. So I'll probably have it go up after class on Monday. But whatever time it does go live, you'll have 48 hours from that moment to do it.
Gotcha.
All right, and you know it's open book because it has to be. But you know, if I find my exam questions on Chegg, I am going to come after you. I'm expecting you guys to do your own work, so please don't disappoint me. All right, folks, I'll talk to you later. Have a good weekend.
Okay.
Study hard.
All right.